Okay, so what I want to do is Stokes theorem, it's 6.8, and then we'll do the divergence theorem. Essentially, what it says is that if you want to find the work done by a force field over a curve C, then instead of doing the single integral like you have been doing, so this would be f of r of t dotted with r prime of t and all that stuff, integral over c dt and all that. Instead of doing that, what you can do is you can actually do the surface integral instead if c is the boundary of a surface integral of the curl of f. So the idea is this: suppose you have a uh, curve in space, like, I don't know, suppose it's going to be closed curve. So f is not a conservative field in this case, because if it were conservative, then your work would be zero around this. Okay, so C is this closed curve, and then you have F is a vector field going through it somehow. Okay, maybe it's doing this, I don't know. Okay, and what you want is you want to find the work done, F dot dr over C. Okay, if the curve is the boundary of a surface, so you maybe have some surface up here. If it's the boundary of some surface, say you have a surface here, then what you can do to find the work done is kind of bizarre. You can actually work with the curl of the function of the vector field, curl of f dot ds over s. So you can actually do the surface integral of the curl of f instead of finding the line integral. So you have a line integral here, and you have on the right side a surface integral here. So the really cool thing about this is that it doesn't matter what the surface is, as long as your curve is the boundary of that surface. So what you could have is you could have a curve like this, like a nice circle or oval or something like that. And your boundary curve can be like this, or it can be, your boundary surface, your surface for which C is a boundary, or it could be like this, So you could have something like z squared equals negative x squared plus y squared. You could have a cone where C here, this curve, is the boundary of that cone. Or it could be that the surface you want to use is this hemisphere. X squared plus y squared plus z squared is equal to 1, where, okay, the hemisphere, z is greater than or equal to 0. Okay, so when you do this, they're going to give you S, okay, in the homework. So you don't have to figure out which one to use. So don't worry about that. All right. So what I want to do is I want to do a problem here. I want to do number 13 that's in the book. And in your homework on Stokes theorem, the last problem is number 15. And so this will help you out in doing that one. Okay, so it says verify Stokes theorem is true. So Stokes theorem, let's go over the conditions. All right. So the conditions: S is a piecewise smooth oriented surface. Oriented means they discuss orientation of a surface here. The orientation of S induces the positive orientation of the boundary curve. This means that if you walk in the positive direction around C with your head pointing in the direction of N, then the surface will always be on your left. So essentially, you have your boundary curve down here. I'll do it in red. Like that. You have your boundary curve down there. And if you're walking along the surface, there's this little man here. If you're walking along the surface, then the surface is always to your right, to your left. So here you are. Okay. You've lost weight. It's pretty skinny, this guy. So if you're walking along the surface, now notice if you look down onto the curve, that's in the positive direction because it's counterclockwise. So if you're walking along the surface will be on your left. It's just like we said with curves, right? If you have a curve and as you're going along the curve, if the region inside is on the left, then that's the curve is positive. The orientation is positive. Okay, so the idea here is that, and I missed a good important point here. N is pointing up, the direction of your head. All right. Okay, so that's one condition that you need to use Stokes' theorem. Okay, so S is an oriented piecewise smooth surface that is bounded by a simple means it doesn't cross itself. The curve doesn't cross itself like that. Closed piecewise smooth boundary curve C. Piecewise smooth means that there's no kinks in it. If there is a kink, then you have to split it up into different curves. Okay. All right, so it's smooth. And then positive orientation, we talked about that. F is a vector field whose components have continuous partial derivatives. All right, that means that P sub x is continuous, P sub y is continuous, Q sub x is continuous, Q sub y is continuous, R sub x and R sub y. Because we're going to say that F is like PQR like before. All right, on an open region D. Okay, so this is Stokes' theorem. So let's try this out. Let me grab this and let's try this out with that problem that I told you about. So I'm going to grab this and let's take it over. We're going to do both sides of this. And the good news here is that in doing both sides of this, I'm helping you out with section 16.7 because 16.7 requires you to do surface integrals. And the right side of this is a surface integral. All right. So it says verify Stokes' theorem is true. So what that means is you have to do this piece and this piece both, and you have to make sure that they're equal. All right, so let's write down F. So F is negative y, x, and negative 2. All right, and then S is the cone. S is the cone, z squared equals x squared plus y squared, where z is between 0 and 4. So what we have is we have this cone. Let me draw the cone in blue. Like this. All right. Okay. And let's see. So the cone is going to be let me draw this a little better. The boundary of this cone is this curve up here. Right there. So that's C. And it says it's oriented downward. So that's the negative orientation of the cone. It's oriented downward. So this is the N. The orientation is down. And so what happens here is that the curve is actually moving in the negative direction as you look down upon it. So in order to use Stokes' theorem, we're going to have to put a negative on these, a negative on this here. All right. So what I'm doing right now is I'm doing the left side. I'll do the left side in red. All right. So let's parameterize this curve. So left side. is integral f dot dr over c. So you did this on the test. You have to parameterize the curve. This curve is, okay, so it's a circle, so you know we're going to have cosine theta and sine theta involved, right? So let's see, r of t will be, it looks like it's going to be cosine t, negative sine t, and then the z component's always 4, because it stops at 4. It's negative sign because it's going in the opposite direction. So let's check that out. Let's look at t values. When t is 0, r of t is 1, 0, 4. So that would be like maybe, I don't know, right there. And then when over 1 up 0, yeah. And then when t is pi over 2, we get 0, negative 1, 4. So we're going back in the y direction. So that would be like somewhere over here. So you're going that direction. Yeah, so it works. All right, so I verified that my R of t is correct. Okay, so now we just do, go ahead and write down the formula. It's f of r of t dotted with r prime of t dt, and 0 to 1, this 0 to 2 pi, I think, right? Yeah, 0 to 2 pi. T goes from 0 to 2 pi. All right, so 0 to 2 pi. My function is negative y, x, and negative 2. So when I plug that into, I'm using this, and I'm going to plug the r of t into that, I get negative y would be sine of t, x would be cosine t, and z is just negative 2 regardless. And now r prime of t, I'm going to dot it with r prime of t. So this is r prime of t, so that would be negative sine t, yeah, negative cosine t, and then what? And then 0. Good. All right, so what do we get here? We get negative sine squared of t, negative cosine squared of t, and then plus 0. So this is dt. All right. All right. So, wait a minute. Time out. I just made one slight error. The radius of the circle is 4, because this is at z equals 4. So I need to put a 4 on these guys. So there's it's just a small error. So 4 cos, and then 4, negative 4 sine. And now this would be 4 here, 4 here. And these will be on 4s here. And so what I get is 4 times 4 is 16 on both of those. So this will be 16 sine squared t. So negative 16 sine squared t. And then, yeah, negative 16 cosine squared t. All right, so I can pull out a negative 16. This is 0 to 2 pi. Negative 16, and I get sine squared plus cosine squared is 1. dt, 0 to 2 pi. So it's negative 16 times what? Times 2 pi. So we get negative 32 pi. And there's our answer. Okay. All right, so whatever this force field looks like, I don't know what the force field looks like. Who knows? There's F. It's got a bunch of arrows going. The work done on the force field on a particle going around this circle, it's going to be negative. So it's working against it, against the path. All right, now let's do the other side. All right, so I'll do the other side in orange. So it's the right side. Right side. So it's a double integral over S of the curl of F dot ds, like this. Okay, so let's find the curl of F. So the curl of F is negative y, x, and negative 2. So F is negative y, x, and 2. Negative 2. Yeah. All right, so the curl of F is, okay, so you do your the partial respect to x, partial respect to y, and partial respect to z, and you cross that with negative y, x, and negative 2. So we get, let's see, 0 minus 0, 0 minus 0, and 1 plus 1. Oh, you just get 2 out of this. Yeah, 0, 0, 2. All right. So we get 0, 0, and 2, like that. Okay, so now what you need to use is this it's a formula from section 16.7. All right, so let me pull it down and I'll explain it again. Where are we at? Well, let me put it down here. So this is how you do, so what we're doing is we're doing the curl of F dotted with ds here. So instead of this piece here, it'll be the curl of F. The curl of F is its own little vector function as well, okay? So it's okay. So this P, Q, and R are not, so in whenever you do the homework in 16.7, P, Q, and R are going to be the components of F, but now P, Q, and R will be the components of the curl of F, because the integral that we're doing is the curl of F dot ds. All right, so here, the curl of F is P, Q, R. P and Q are both 0. And R is just 2. So if we apply this, we get equals double integral of negative 0. Okay, partial, okay, it's going to be 0, but I want to go over this so that we can get it down. All right, so in case it wasn't 0, in case it weren't 0, let me show you what you would put here, okay? Remember that we're dealing with a cone, and that cone is z squared equals x squared plus y squared. So z itself is, if you get z by itself, so what I'm trying to do here, in fact, let me not do the integral just yet. Let's talk about g first. So g of xy, that's just z, and z is the square root of x squared plus y squared. It's that cone. All right. And so this is x squared plus y squared to the 1/2 power, right? And so the partial of g with respect to x would be 1/2 times 2x times x squared plus y squared to the negative 1/2 power. So this would be x over square root of x squared plus y squared. So that's what would go here. And then g sub y by symmetry would be y over, yeah, exactly. Exactly. That's what would go there. Go here. All right. So we don't need to worry about that because q and p are both 0. So when we do this integral, we'll get double integral of -0 times g sub x. I'll just write g sub x there. Minus 0 times g sub y, what we found there. And then plus r. Okay, so r was 2. So plus 2. And then it's dA. dA over d. So let me clean this up and I'll talk about this. So this is double integral over d of 2 dA. Now, it's not quite what we need just yet because in order to use Stokes' theorem, sorry, I'm probably making you dizzy by going back and forth like this. In order to use Stokes' theorem, C has to be positive orientation. So if it's a negative orientation, you have to multiply by a negative. So you multiply all this by a negative. And so we get a negative outside. All right. And then this D, okay, so what is D then? D is the shadow of this surface down in the xy plane. So D is down here. This is D. So D is just the circle x squared plus y squared equals 4. It's the shadow of this region inside. All right, it's a projection down. I shouldn't say shadow, it's a projection. All right. So this would be, instead of D there, I'm going to put x squared plus y squared equals 4. And then dA will be dy dx. Okay, now on the test, I had several people write, they would do this, double integral, and they would say, okay, x goes from -2 to 2, and it looks like y would go from negative square root of 4 minus x squared to positive square root of 4 minus x squared, and then 2 dy dx. Now, what's an easier way to do this? Yeah, I use polar. So this is a mess. So, I mean, you can do that, okay, and plenty of people did, but what they got was usually wrong. Why? Because it wasn't this simple. There was some other nasty function in there. And then plugging all this business in was not fun. So I'm not saying you can't do it that way, and I'm not trying to shame you if you did. I'm just saying it would be easier if you just use polar. That's what they're for. This is negative integral. In fact, yeah, 0 to 2 pi, and what? 0 to 2, and then what? Yeah, exactly. Okay, so I pulled the 2 out. All right, so before we do this, actually, there's an easier way. What we're doing is we're doing this integral. There's no x or y there. So we're just integrating over the circle. So it's just the area of the circle. But we'll go ahead and do it. This -2, this d theta, this comes, 2 pi comes for free. And then it's 1/2 r squared from 0 to 2. So this is -4 pi times 4 over 2. What's this? Oh, R is, I'm sorry, it's 8. Yeah. It's, hang on. Yeah, I screwed up somewhere. Um, this is 4 over 2. Oh, I'm sorry. It's not 0 to 2. It's, this is 16. I got confused because when you parameterize this circle, yeah. Z goes from 0 to 4, so x squared plus y squared is 16. 4 is correct here, but this would be a 16 here. So when I drew, where was it? This here, this is not 4, this is 16. Yeah, okay, sorry about that. Minus 5 for Zuka. That's 16. This is now a 4. And now this is 4. And now that's 16 over 2, which is 8. And now this is negative 32 pi, which is the same exact answer as we got previously, this way. All right. Okay, so it kind of looks like this way was easier, but a lot of times it's not. So it's good to know Stokes' theorem. In fact, whenever you do the problems, you'll see that trying to do it directly is pretty difficult. All right. So that's an example of Stokes' theorem in action. Do you have any questions? I'm just walking through this, not even asking you if you have any questions. Anybody have any questions? All right, you're doing okay. No, okay, everybody's fine. Okay. Um, okay, okay, cool. All right. Um, what else needs? Yeah, wait. Say that again. Yeah, yeah. Well, we took care of that though, right? Because we put a negative in there. Because Stokes theorem really only works, it only works for positive orientations. So if it's a negative orientation, you have to put a negative on there. And you'll see that in the homework. That's where this negative came from. All right. Let me see here. Let me see what else I have to go over. Um, this is just stuff and some other stuff. There's examples. So here's a good example of why Stokes theorem. Um, let's see. F.dr occurs in section. See here, what you could do if you're trying to find F.dr, integral F.dr, is of this curve C. So you're walking around this curve in a positive orientation. Is you can use the cylinder instead. So you can use the cylinder, x squared plus y squared is 1. Let's see, f.dr, it might be kind of complicated to work with this circle. Oh, yeah, look. Yeah, I see here, this circle is hard to parameterize. So you'd have to parameterize the circle using R of t, but it's some sideways look. Well, it's not hard to parameterize actually, because it's just a mixture of z equals 2 minus y, and the cylinder, it's going to be the intersection of those two. So what you'd have to do is parameterize the cylinder as cosine squared, cosine t, sine t, and then the cylinder, you would use a z there. So I'm parameterizing the cylinder using what we did in 16.6, parametric surfaces. So it's a circle, and it's circles of radius 1, and then for every z value, there's another circle. This actually would be a good problem on the final. So do you see how I parameterize this cylinder? So the cylinder like that, see? It would be parameterized like this. All right. And then the circle, that ellipse, would be z equals 2 minus y. That's the plane, and so I would plug the sine of t in for y. So we would get z equals 2 minus sine of t. That is that circle. Z equals 2 minus sine t. That's interesting. Huh. Okay. Anyway, so then you would that would be your RT. All right. So moving along, they ask you to compute this integral. So you can go both ways. If you need to find the double integral of the curl of f, if you need to find the surface area of the curl of f, you can actually use f dot dr instead. So if this is difficult, you can actually do the work integral instead. All right, so let me move on to the divergence theorem. So the divergence theorem comes in to play whenever you are trying to find the surface integral over a surface of a vector function. So remember what this is. The left side here is the flux. So let me just remind you what's going on. So you may have some surface, I don't know, maybe it's a hemisphere. And you may have some vector field going through that surface somehow. Maybe it goes like this. All right. And so it's going through the bottom part as well. All right. So the flux is the amount of the vector field going through the surface itself. So if the vector field is perpendicular to the surface, like it is here, there's a lot of flux. So flux is great. All right. If it's this here, it would be less flux there. All right. So in 16.7, you have problems like this. And what you have to do is you have to split these surfaces up into two different surfaces. The bottom one, that's the bottom one, and the top one. And you have to do two different surface integrals. Double integral of f dot ds over s1 plus double integral of f dot ds over s2. And if it's composed of three surfaces, then you got to do three surface integrals. Do you understand? All right. So what divergence theorem says, there's another name for this. It's also called Gauss's theorem if you're in physics. It says, forget this. Don't do it that way. Do the triple integral over the divergence of f. The triple integral of the divergence of f over the solid. Remember, this E is the solid. I can't draw on it. So There. So instead of working on the boundary of this, the boundary would be the hemisphere, well, the exterior, and then this bottom part here. Instead of working on that, we work on the interior instead. Just what's inside. Just what's inside. So that's a lot easier because the divergence of f, remember, divergence of f is very simple. It's just the partial of p with respect to x. My computer's getting hot. Hang on, let me plug in the fan. So what it says is, remember the divergence of f is p sub x plus q sub y plus r sub z. So this turns out to be usually very simple. All right. Okay, so here's a good example of what I'm talking about. Oh, well, let's look at the conditions. So E is a simple solid region. A simple solid region is one that can be described very simply using all it can be described very simply using X, Y, and Z. All right. It doesn't have some like really complicated formula where you have to use implicit functions. All right. And S is the boundary surface of E. So the boundary surface, not the boundary curve, but the boundary surface of E. So it's the outside part. All right. Let F be a vector field whose components have continuous partial derivatives. We talked about that before. In an open region that contains E. So then this is the divergence theorem. I'll give you this on the test. I'll give you this on the formula sheet. All right. So a really good example of this, of how much easier it would be, is to look at example 2 here. So example 2 says evaluate the double integral of f dot ds. This is the flux of this vector field. So there's some vector field going through this. Whatever, who knows. And S is the surface of the region E shown above. So this is S is this surface. Well, let me use a different color. It's the exterior of this. It's this, and then all of this, and then the bottom as well. And then the sides as well, the back side. So there's 4 different surfaces. S1, S2, S3, S4. So doing this flux integral involves 4 different surface integrals. And the problem with that is that you got to sit there and figure out what all of these surfaces are parametrically. All right? Well, not necessarily, but you have to sit there and find your g of xy or g of yz for all of them. And then you find your n from that and stuff like that, okay? So it gets to be complicated. So what you do instead is you just do the triple integral of the divergence of f. And it comes out to be a lot easier. All right. So let's just do that real quick. Let's do this problem just real quick. All right. So I'm not going to do the left side. I'm just going to do the right side. So let me cut this out. While I'm doing this, is there any question? Oh yeah, definitely. But I mean, I would expect you to use the simpler way. In fact, well, I'll show you in a minute when we're done. All right, let me get that figure. I'm just going to set up the integral. We're not going to do it in time. All right. All right, so here's the surface. All right, so instead of doing 4 separate double integrals, or surface integrals, excuse me, we're going to do the triple integral. So this whole thing is, the interior of this is E. The triple integral over E of the divergence of F, the divergence of F dV. All right, so let's figure out the divergence of F first. So the divergence of F will be P sub x plus Q sub y plus R sub z. So divergence of F, all right, you tell me. Oh, y plus 2y, and that's it. So 3y. Much easier to work with than this nasty thing. Okay, so just 3y. So this is a triple integral of 3y. Okay, so now we have to figure out the limits of integration here. All right, so I am going to work with y first because a lot's going on in the y direction. So it'll be dy. So y goes from this back part here to this front part here. So it goes from that to that. So you're right, 0 to what? Yeah, 2 minus z, exactly. All right, now we'll do z, dz. Okay, so z goes from the bottom. Yeah, exactly. Yeah. So z goes from 0 to 1 minus x squared. And now, what does x go from? Yeah, well, yeah, exactly. So it goes from -1 to -1 to 1. All right. And yeah, this is it. And so you just do this route. Okay. So the rest is trivial from here. All right. It's just a triple integral. Did I just say this is trivial? And when you first look at this course, like if you're in Cal 2 and you look at a Cal 3 problem and you look at this, you're like, what the heck? But now you know that it's just trivial to do it. You just do each one separately. Okay, so I want to show you something. Um, I've got to go back to, I'm going to show you something from the test that was kind of odd to me, why people were doing it. I'm looking on my other screen. Let me pause the video for a second. All right, so here's the key to the test. Let me see if I can make this bigger. All right. By the way, I screwed up, but these two vector fields were the same. I don't know if you noticed that. So we go and go and go. All right, it's the last problem. Right here. So if you look at it, it says f is a conservative vector field. So you can find a potential function f, which a lot of people did. You did a great job on this. A lot of people did this. And then it says, using part A, find the work done. Well, look how simple this is. Shoot, come back here. Look how simple this is. If you use, so what I'm using here is if you have the integral of f dot, let me go back further. If you have the integral of f dot dr over c, then if f is a little f is a potential function, oh, I wrote it here. What am I doing? It's this. then you can just take your potential function and plug in your R values, and you're done. What I saw a lot of people doing was going through all this hard work of this integral f dot dr is integral f of r of t dotted with r prime of t. This is a lot of work, okay? So if you can, use the potential function. That's what it's there for. It says using part A. I didn't count off if you did it this way. I really just felt bad if you did, to be honest, because it's a lot more work. And it was almost a miracle if you actually got the right answer from that. So once again, I mean, I'm not saying, I'm not shaming you for doing it whatever way you did it, but I'm just saying, just, use what you got, All right. Any other questions? So, all right. So that's the divergence in the Stokes theorem. And so there you have it.